All right, let's jump straight into this explainer. We are looking at a really fascinating anomaly in AI today. You know how we can generate literally perfect images in just a handful of steps now? Well, ask the exact same math to generate text and it completely falls apart. It's wild. Welcome to the geometry of AI.
So, if you follow AI news, you've probably seen that deterministic few-step generation is frankly everywhere right now. Techniques like consistency models, progressive distillation, and rectified flows are churning out these stunning, high-quality images in just 1 to 4 steps. They basically learn a super smooth map from pure noise straight to the data. But when we try applying that exact same deterministic method to continuous text latents, total catastrophic failure. The output just turns into this bizarre mess of repeated tokens and random multilingual fragments. Well, unless you force the model to turn through like 32 or 64 steps. So what's going on here? Why the massive gap?
The contrast between these outputs brilliantly illustrates the paradox right away. With images, you get a smooth, perfectly accurate, gorgeous mountain landscape generated almost instantly. But look at the text equivalent, produced in the exact same number of steps. It literally just spits out garbled characters, random fragments from different languages, and broken, repeating tokens. I mean, it's totally incoherent.
Now, at first glance, you'd probably assume, oh, this is just a scaling issue, right? Or maybe we just haven't trained these text models enough yet. But actually, a really rigorous geometric analysis definitively rules out all the usual suspects. The research we're diving into proves that this failure, it is not a lack of training data, it's not a poor architecture choice, and it's definitely not bad scheduling. The problem is fundamentally structural.
So what is the culprit? It turns out it's entirely geometric. It's governed by a property researchers are calling decoder sharpness. See, generation relies on a transport map to move from noise to a recognizable output. The reason these text models fail in a few steps isn't because the model lacks transport accuracy. It's actually because the model hits a really sharp categorical readout. Basically, it hits a discrete branch choice where it has to decide on one specific hard token. And that boundary is simply too sharp for a smooth map to resolve quickly. Think of it kind of like a blurry dartboard. With a smooth, continuous color wheel, like we have for image latents, being a millimeter off with your dart just gives you a slightly lighter or darker shade of blue, right? Totally safe. But put that on a sharp text grid, and that exact same tiny error pushes you completely across a hard decision boundary. You cross that invisible line, and the system totally flips the token from a word like work to something completely different and incorrect. Because text has these unforgiving, discrete boundaries, a smooth, deterministic map mathematically just cannot resolve the ambiguity in a few steps. It ends up delivering a state that has a slight fuzzy blur to it. Now, an image model, it can easily absorb that blur, but a text model takes that exact same blur, lands right on a sharp decision boundary, and breaks. It leads to an absolutely unavoidable collapse. To actually prove this geometric limitation is happening, the researchers introduced a pretty fantastic diagnostic metric. They call it DAVI, which stands for Decoder Amplification of Boundary-Aligned Inputs. Basically, DAVI measures exactly how much a decoder amplifies small, structured displacements right near those sharp decision boundaries, and then compares that against just random, standard noise of the exact same size. It's literally a sharpness meter. And the data from this metric is our smoking gun. Just look at the difference in these numbers. Across 4 families of published image decoders, like Lumina and Flux, they score a DABI of roughly 1, meaning they safely absorb boundary errors, just like they'd absorb random noise. No big deal. But then look at the text decoders. The continuous text decoder ELF amplifies those boundary errors by over 500 times. And it gets crazier. Other models like Langflow and Cosmos have DABI numbers well over 10,000. There is absolutely zero overlap between images and text here. To see this sharpness actually play out on the ELF model, you just have to look at what happens when you introduce even a tiny boundary-aligned error. It massively spikes the token error rate. We're talking flipping up to 77% of the tokens. Meanwhile, if you apply random isotropic noise of the exact same size, it barely registers above 0%. So the text decoder is incredibly sensitive, but only to these specific geometric boundaries. All of this comes to a head right at the terminal step of generation. Both image and text deterministic models output what's known as a posterior mean blur right at the very end. But while smooth image decoders happily accept this blur without degrading the final picture at all, the sharp text decoders completely fracture it.
That tiny fraction of blur pushes the latent state right over those sharp boundary lines, and boom, perfectly good continuous representations turn into incoherent token errors.
And the math holds up perfectly under stress testing. The researchers ran an Oracle roll-in, mapping out exactly how tokens flip across different step counts, like 4, 8, and 16 steps. And notice how the token flip rate collapses entirely onto a single, predictable curve based purely on the noise level. This is a huge finding because it definitively proves the limitation is fundamentally geometric. You can't just fix it by tweaking your training schedule. The literal geometry of the readout dictates the failure. So, if smooth deterministic maps are mathematically doomed when it comes to text in a few steps, how do modern AI generators actually, work? Well, let's look at two proven escape mechanisms that allow models to successfully generate text by intentionally stepping outside of those smooth deterministic bounds.
The first escape route is categorical commitment. You see this all the time in autoregressive models like Llama 2 or Quen. Now, interestingly, these models actually have DABI scores way higher than the ELF model we just looked at, meaning their readouts are incredibly sharp. But they succeed anyway. How? Because they make a hard, discontinuous jump. They lock in a discrete token at each and every step and irreversibly commit to it, completely sidestepping the continuous bounds that trap the few-step models.
And the proof is right there in the ablation studies. Researchers tested a masked diffusion model and simply removed that hard commit step, keeping the sampling and everything else exactly the same. Without categorical commitment, the text generation completely collapsed into gibberish. It caused a massive 5x spike in perplexity, jumping from a really solid 7.3 all the way up to 38.6. So yeah, commitment is an absolute necessity here.
The second escape mechanism is what they call stochastic reinjection. Instead of relying on a deterministic path, an ODE, you use a stochastic differential equation, or SDE. Basically, this injects fresh noise at every single step, which allows the model to sort of organically bump out of those sharp boundary errors. When they tested this on the exact same ELF model in 4 steps, the deterministic ODE failed terribly with a perplexity of 294, but simply by switching to an SDE sampler, the perplexity plummeted to a very respectable 50. It's a real game changer. When you put all of this together, it creates this incredibly powerful predictive taxonomy. If a system has a low DABI, meaning a smooth readout and zero categorical commitment, it works. Those are our image models. If it has a high DABI, so a sharp readout, and zero commitment, it fails catastrophically. Those are the deterministic text flow models we've been talking about. But if you have a high DABI and high categorical commitment, the model safely escapes the geometric trap. And those are our successful autoregressive text models. This whole thing leaves us with a pretty profound realization. This failure in fast text generation, it is not just a software bug we can easily scale up or train away by throwing more compute and data at it. It is an irreducible cost of geometry. You literally have to design models that step outside the deterministic continuous class to make text work. So the question I'll lead you with today is, how will this absolute mathematical boundary dictate the next generation of AI architectures? Thanks so much for joining me on this explainer, and I will catch you on the next one.